All right. All right, so let's go. A couple things. Homework's been posted because we're right at the end. This is binomial Poisson probabilities. Let's open this up. I put the due date on Monday after lab, so you can work on it over the weekend. You can do it in lab. It really is, calculating probabilities using the dbinom function and so forth, and then doing like these frequency tables, like expected numbers and coefficient of dispersion and so forth. So that's been posted because we are finishing that up today. All right, so that's up. The second thing, make sure it's available. I think it did. Don't know if you saw it, but the application part of the exam, the grades have been posted in Blackboard. You're going to get the theoretical part at the end of class. Exams were okay. As expected, the application grades were higher than the theoretical part. I would say make sure you look back through the presentations and know definitions, terminology, and stuff. Definitely look over, identifying nominal versus continuous discrete variables. It plays an important role in determining what types of tests to use, and those types of tests will come up again near the end of class for the final exam. You'll see this work again. You'll see it again. So we'll get it back. The key is, so here's the key for the application. I'll put this outside my office. You can check it out. If you have questions about it, you could ask me about it. The key for the exam, so if you click on the quizzes and exams, you'll get the key. You'll get mine. I think the only part of it that might throw you off a little is this one, histogram. So I did say adjust the number of bars until you think it looks good. So just the default looks okay. And if you just did histogram Q5 of your tarsus, it's going to produce a decent figure. You could always increase the number of bars, set the breaks, and I think it was like if I did breaks equals 5, I think it gave me lists. If I did breaks equals 6, it gives me the next jump. So it's like anything from like breaks equals 6 to maybe like breaks equal 12, maybe. You get this transition. So the next one up where it like doubles the number of bars would also be okay. It's just not a huge sample set, huge data set, so this could work. So I was just really making sure that you knew how to make a histogram. That's what we were looking for, and everything else looked okay. Some of you, to load the car package, this is how we load the car package. Some of you actually use data, bfox, comma, car in quotation marks. That loads the data file. It doesn't load the package. So we're going to have some items where we have to load the package. So make sure you get this down for the library car. And then if you didn't get it loaded, properly when you knitted, you would get an error because the car package wasn't loaded. It doesn't know where to get that bfox. And it wasn't like if you did the data, bfox, comma, car in quotation marks, and did the rest of these, I didn't take off. The only thing you didn't do was load that car package. So check it out. As I said, grades were okay. Nothing seemed to stick out. That's also what I meant to say in my ecology class. A couple of you are in there. Yeah, normally what I do is when I go through the exams, I look for specific questions that the majority of people miss, and then I go back and look at them to see if maybe I screwed up. One year I didn't post the correct data file, so the answers, like the first couple answers, were wrong. And it's like I'm comparing my key to what I was getting. It's like, where are you getting these numbers? And then I look at it, it's like the code is right. I have no idea what's going on. And after like the third exam, I went back and looked at the data file. Yeah, I changed the data file. I had those on the computer, but I uploaded the old ones. So it happens, but I do look at it. So if you have questions, feel free to come and ask me about it. Also check the keys for the answers. All right, so which distribution should we use? So we're talking about discrete distribution. These are ones where the items are numbers, whole numbers. That was actually on the exam. What's a discrete versus continuous? Discrete is restricted. It can still go from infinity to negative infinity. It can be infinite number. It could be we can say, let's say, unbounded. It's more restricted to specific values, which whole numbers. All right, so we've got binomial and Poisson. The first one, we want to model the number of bad brake pads that get produced in an assembly line in a day. What would we use?
Binomial.
What's that?
Binomial.
Why binomial?
Because it has a set time limit.
Okay, but do we know how many pads were produced in that day?
No.
So number 2 is the second one. Number of bad brake pads in a batch of 100. Now this 100, so you're right. I said it did it for a reason. In a day, we did define a time period. We did a limit. That's not our out of number because our out of number is related to the number of bad brake pads. We don't know how many we made. Are we making 500 brake pads in a day? Are we making 10,000 brake pads in a day? We don't know. So it could, in theory, be a large number, but if we're producing 10,000 brake pads in a day and we're asking, what's the chance that we get 5 brake pads out of that 10,000? Now it's a rare event, and thus we don't really have an out of number. That's how we kind of set things up. So don't be mistaken by that in a day, because we can define time period, time frames. Seconds between lightning strikes. What would that be? So I should go back. This is Poisson. The brake pads in a day is a Poisson distribution. Number of brake pads in a batch of 100, there's our out of number, that's a binomial. Seconds between lightning strikes. Yep, Poisson, so it could be infinite number of seconds. Number of home runs in 15 at bats. Binomial. Our out of number, 15. Age of first infection. Oh, hold on. Number of home runs in 15 at bats. If we change that to a Poisson, it would be number of home runs in a year. Because we don't really know how many at bats they've had. All right, we don't have an out of number of at bats. And that would be the equivalent of saying in a day, in a year, in a season, maybe in a career, and so forth. All right, age of first infection. Say age of first infection with a rhinovirus or something like that. Yeah, Poisson. You have individuals that might not have been infected. Time of death. So this would be an experiment where we expose an individual to a contaminant or to an infectious agent, and then you measure time to death. Binomial? Poisson. Poisson. Right? This is classic survival analysis utilizing Poisson distributions. Number of offspring that survive to maturity. Poisson, and then number of offspring out of 1,000 that survive to maturity. Binomial. So here, again, 2 different things. We don't know what our out of number is, but as soon as we say out of 1,000, so you can say number of offspring that survive to maturity in a clutch. We didn't define how big that clutch is. Could be 1,000, could be 10,000, could be 3. All right. So that's what we're looking at. That's what we're looking at. You'll have something on the exam, on the application part, or not the application part, the theoretical part, where I'll have a couple of these scenarios, usually maybe like four or six, and each one will be worth like a half a point. Like if you really just don't get this part, I don't want to make it 6 points because our total theoretical part's only at like 30 to 40. To make it reasonable. So that's why, like on this first exam, the rounding part, each of those was worth half a point. Variable, each answer was worth half a point. All right, any questions on these? So we will return to these when we get to our continued goodness of fit tests. But we introduce it first because it gives us a little bit easier understanding of probability and probability across all possible outcomes. All right, where we're going is getting to the continuous random variables. So these continuous random variables can take on any number between our bounds. So any decimal numbers, and I think I counted that. If you said continuous variables could take on any decimals and discrete or whole numbers, we did that. I counted that. So these would be chapters 5 and 6. Now, in chapters 5 and 6, we're not really going to be covering all the other distributions. We're going to see a t distribution. We're going to see f distributions. We're going to see chi-square distributions. Those are all continuous distributions. And we'll introduce those distributions when we get to the statistical tests that utilize them. What this will be focused on are normal distributions. So introduction to the continuous distributions and then the normal distribution itself. All right, so for continuous distributions, our probabilities are modeled in a slightly different way. We still have this curve. All right, so let's move that. This would be an example of a probability curve. All right, and you saw me diagram a curve with like a binomial and Poisson. So I did it the same way. But those curves were smoothed out. If you remember, I said the curve, as we model it as a curve, but in reality, it's more about histograms because you've got discrete numbers. You can't have 1.5 offspring. Continuous, you can't. You can have that 1.5. You can have that 1.55. You can have 1.56789. All right. So our curves, instead of representing exact probability, is now more about a probability density function. All right. It's a probability density function. The probabilities themselves of a specific number is going to be represented by the area under the curve. And that's a little bit different. So if we looked at, let's say, a Poisson distribution, you have a histogram, that's 1, your probability of 1, and then we may have probability of 2, and then we'll go up probability of 3, and then a 4, and then 5, 6, and so forth. So you've got these curves. And if I ask what's the probability of 1, you just look at the height of that curve, or that height of that bar. That gives you the probability. Not so with a continuous distribution. For continuous distribution, we actually have to look at an area under the curve. Why? Well, it's based on our definition of a continuous variable. Our continuous variable can take on any number, including any decimal number. So if we ask, what's the probability of getting this exact number? It's actually very, very, very small because we could be at the 890, we could be 891, we could be 89001, and so forth. So collectively, the probability of getting this exact number is basically 0. It is super tiny. So we can't enter in any equation to get this value. We can't enter this value into some equation to get that probability. But we can say, if we want to get this, we're going to go really close around it, And that'll give us a very thin slice that we can then figure out, okay, well, what's the area underneath this curve? And we'll use that to approximate our probability. All right, so the area under the curve actually does have an equation, and that equation is called the cumulative distribution function. There's one for the normal curve, there's one for every continuous curve that's out there. All right, with this so here's our curve. I've marked off this area. This would be the area under the curve between 5 and 10. So this would represent the probability of getting a number between 5 and 10 if we were doing a continuous distribution. This area that's unshaded has a probability, and this area from 10 all the way up to infinity also has an area. What we know is that the sum of all of our probabilities will have to equal 1. So on these curves, the area underneath the entire curve will be 1. And we can use formulas to calculate it by hand. All right, we could use R to do it, and we will be using R to do some of these probabilities. All right, or we can use statistical tables, and we will use these statistical tables. I'll show you how to use these tables because, one, I think it's an important skill to have because you might not have a computer here, but number two, you may get asked to do it on a future exam beyond this course, I should say. All right, so continuous distributions that we'll see include the t-distribution, the chi-square distribution, the f-distribution, and the normal distribution. The t-distribution is used for doing like a t-test, student's t-test. All right, we'll introduce you to that. But we also use a t-distribution when we calculate 95% confidence intervals. All right, so when we get to the confidence intervals, I'll introduce the t-distribution. The chi-square distribution is used when we perform a g-test or a chi-square test. Both of these, g-test and chi-square test, are goodness of fit tests. So with our discrete distributions, we'll use those probabilities to get our expected value, and then we can use a g-test or a chi-square test to determine if our observed matches our expected value. We could also use a chi-square distribution to generate confidence intervals of the variance. Now I have this as time permitting. We never have had time permitting for this. There's actually other stuff that I'd rather move to. But know that we do confidence intervals of the mean with the t-distribution. We could do the same with the variance. So if we were interested in generating confidence intervals for, let's say, the variance of a tooth length, we could do that. And if you have to do that, come talk to me. I can help you out. F-distribution is the test distribution that we use in the analysis of variance and a couple of our variance tests. All right, so ANOVA is comparing means. We have some variance tests that will test to see if we have equal variance between our groups. And again, F distribution was Fisher, Ronald Fisher, and when we get to these, I'll introduce the F distribution and tell you about it. What we're going to focus on today is the normal distribution. Normal distribution is that bell-shaped curve. Bell-shaped curve. If we have large sample sizes and repeated experiments that produce those large sample sizes, our means, the collection of the means for each of our samples, should approximate this normal distribution, which then allows us to utilize these distribution, F distribution or T distribution. So this kind of relies on the underlying assumptions. We'll also use the normal distribution if we have a one sample test. We collect a sample, we have our average, and we say, is our average equal to some value? Or is our average greater than some value? This is when we would use the normal distribution. If we have two groups, when we ask, are the groups means equal, we're going to use the T distribution or the F distribution. All right, so one sample test of means for a population, and not a sample, where we are comparing our mean to a specific value. So what is the normal distribution? Normal distribution is this bell-shaped curve. Right? When we use it for a test, or when we assume our means follow this normal distribution, we're doing what's called a parametric test. So it assumes that our sample means follow a normal distribution. It is defined by our population mean and our population standard deviation. So it's defined by mu and sigma. We've already been exposed to it when we used the R norm. Right, we generated a random numbers from a normal distribution. We define these two values. These two values are both continuous variables. So we can have an infinite number of normal curves. It doesn't have to be that classic shape. We can compress it. It'll still approximate a normal distribution. Or it still is a normal distribution. It just doesn't look broad and everything. If we take our mean and standardize it to standard deviates, which this graphic is, it will look just like this curve. So what are we talking about standard deviates? So on this curve, we represent it by 0 as the mean of our sample, and we ask how far away, how many standard deviations away from the mean are we? So if we convert all of our data into standard deviates, yes, it doesn't matter what the shape of our underlying data looks like, the values and so forth, it's always going to come out looking something like this. This normal curve is unbounded, so it goes from negative infinity to positive infinity. So the area under the curves still sums to 1. We are also symmetric around the mean. So if we calculate the area under the curve from 1 all the way up to infinity, that is going to be the same area under the curve as negative 1 to negative infinity. T's distribution is also symmetric. Also with this normal curve, the mean is going to equal the median, which is also equal to our mode. When we write our normal distribution, when we talk about samples following a normal distribution, we would write it just like this, where x is our sample, and we say it follows a normal distribution with a specific mean and a specific standard deviation. So we'll see this short. I'll write this shorthanded at times, and this is what we're meaning. This also follows the R norm and the D norm and the P norm. Normal distribution has some interesting relationships, and I'd say useful relationships. All right, so if we take our mean and we do a plus or minus a single standard deviation, that covers a little more than 68% of all of our data points. If we do 2 times the standard deviations, it's a little bit more than 95%. And if we do 3 standard deviations, it's more than 99%. It's 99.7%. Or more than 9.7%. So the utility of this is if we were trying to approximate a 95% confidence interval, we could do so by taking 2 times our standard deviation. And that approximates a 95% confidence interval. We won't approximate it. We will actually calculate true 95% confidence intervals, but this makes for a quick and dirty test. If we were looking at the actual percentages, our 95% of the items is actually 1.96 standard deviation units away. So we're going to see this 1.96 reappear. All right, we're going to see this value reappear several times. 50% of the items is 0.674 standard deviations, and 99% of the items is 2.576. You don't need to memorize these. The only ones you really need to know is the 2. 2 times our standard deviation approximates 95%. This is our probability density function. So the likelihood that we draw a value that is close to the mean is pretty high. Because if we're drawing it close to the mean, we're at the peak. The probability that we draw it 3 standard deviations away is going to be pretty small. What we can do is take this curve and do a cumulative probability. So if we were doing quantiles and did 25%, 50%, and 75%, what it would do is it'd start at negative infinity. That's our 0. And then it'd say, at what point do we have 25% of our points to the left of that line? Or what point do we have 25% of the area under the curve? And that's our first quartile. And then we have 50% is our second quartile. 75% is the third quartile, and then all the way up to infinity is our fourth quartile. We can take those percentiles and change it to a curve. So a cumulative density function is that curve where it says as we go up our quantiles, all right, these are the percentages, our probability, that area under the curve goes up very, very slowly because we're far out there, a real low number. And then as soon as we start to hit where it goes up here, now we start getting a rise in our cumulative density function until we hit our inflection point. So the cavity switches. At that spot, that is our 50% point. That's our median. That is also the peak of our graph. All right, and then it slows down and approaches 1. It approaches 1, and eventually gets to 1 if we get to infinity. But again, it's more about when we get to infinity, we're still getting very, very close. I present this cumulative curve because this is what's predicted from a normal distribution. We can take what's predicted, a predicted quantile from a normal curve, and graph our actual observed data against that. So take our observed data and figure out where's our 1%, where's our 2%, where's our 3%. When we do that, we get something called a quantile-quantile plot. And from these quantile-quantile plots, we can assess whether or not our own data follow a normal curve. And we're going to do that. We're going to learn how to do that. All right. So here's an example quantile-quantile plot. We can plot this cumulative density function for any distribution, for chi-squared t distribution, f, and I will. You'll see it in the presentation because it's a good way to show you when we violate assumptions. What we compare it to is a normal curve that has a mean of our sample and a standard deviation of our sample. Now, if our sample is actually normally distributed, then our points should fall on a 1-to-1 line because it says that our observed quantiles match the predicted quantiles from a normal distribution with our sample mean and sample standard deviation. When we violate that, when we don't match that, then we're not going to follow this 1-to-1 line. We'll be curved in some way. So either a single curve or some sort of S-shaped curve and so forth. And we'll use this to assess normality of our sample. All right. So we mentioned standard deviates because that's how our normal curve is typically presented, and where our x are standard deviates. Standard deviate has also been called the Z-score. So if you've had, I don't know if anyone has had statistics yet, you have a math department, they probably talked about like a Z-score test or something like that. That's what they're referring to. Z-score test is this, and we'll do it. We'll do it. All right. So Z-score is our value minus the sample mean minus the sample standard deviation. Here I've written it as the actual value in our population minus the population mean minus our population standard deviation. That gives us how many standard deviations away we are. How many standard deviations away from the mean our data point actually is. When we do this, when we convert all of our values to the Z-score or the standard deviates, it converts our own normal distribution to a normal 0-1 distribution. And this is what it looks like. So we would do this as a way to easily calculate the probability that we would get a value from our sample less than some other value or greater than some other value. All right, this is what's the probability that our sample mean is greater than 5? Well, if we assume that we're normally distributed, we would calculate a z, and then we would actually look at the area underneath the curve. Now, you could say, why would we even do this? Why would we do the conversion first? It's because all of our statistical tables have been created for z's, or these z-scores. So we can use a printed table to estimate it. So under here, here's an example. Of course, they're not accessible because they're tables. So under statistical tables, I have a normal table here. This is as a 0-1 table. And it tells us which area we are looking for. So if I ask, what's the probability that we have a sample mean less than 1? All right, well, there's 1. We want to know the area under the curve to the left of 1. We can use this table right here to do that, as long as we're working with our z-scores, as long as we convert our data to the z-scores. All right, so we're going to learn how to do these tables. Do we have to do this in R? No, when we do these calculations in R, we tell R what our mean and standard deviation is. And then R will do the conversion for us. So doing these things by hand's a little harder than actually using R, but it's not terrible. So what types of questions can we answer using the z-scores and the z-test? One, we can ask, what's the probability of finding an individual smaller than X? So we have our sample, all right, and then we lose it. We lose one of the items, all right? And we find this unmarked item on the floor, and we say, well, maybe this item's part of our sample. We measure the item and say, okay, is this individual smaller than, or what's the probability that we would get an individual of this size based on our sample? That's kind of what that question's asking. What's the probability of drawing an individual that's between X and Y? So we go out and measure it, and maybe we have a range and say, okay, if we go out and resample and we need to get an individual of a specific size, what's the chance that we actually draw that individual? Well, that's a z-score, or a z-score. If we have a sample size that then has a mean of X, then is this sample part of our population? So if we have a sample, we've collected a sample of, let's say, these black bugs that are running around, and we ask, is this part of ASU's population based on the population averages? Yeah, we would do a z-score test. So this part here is hypothesis testing. We'll calculate p-values and compare p-values to answer this question. These first two are just probabilities. These are standard probabilities. But note, in all cases, with these types of questions, we make the assumption that our population is normally distributed. And the test would probably say that. Assume the population is normally distributed. All right, so how do we use the probabilities? First way is using our tables. Two of them are posted. I showed you one. And this is probably the one that I prefer. So here's the one, because let me open up the second one. Here's the second one. Here's the second one. All right, and all of the tables, and you can do a search for normal tables, and you'll find others. I prefer this table because it gives us the entire area to the left of our value. All right, so on this first page, it's from here, whatever our z is, to the left of that point. On the next page, it's to the right of that point. On this graph, this is the area from 0 to our point. So if we ask the area to the left of this line, well, this table only gives us this part. We then have to add 0.5 to cover the rest, because again, the total area under the curve is 1. We're symmetric around the mean, which means half of our area is 0.5. So the area to the left of 0 is 0.5. The area to the right is 0.5. So this one just kind of requires an extra step to calculate our probabilities. So I'm going to use this one moving forward. But I have both for you to use. All right. So this is what it's. On this table, side one gives it to the left of our value. The second page gives us to the right of our value. So how do we read it? We read it as reading down the column and then reading across the row. So these values represent Z. These are the tens digits. And then when we go to the hundreds place, you can see the hundreds digit across the top. So if I ask, what's the probability that we would draw a sample that is less than 1.5, or 1.5. All right, and that would be 1.50. We went to the left of this line. That's all of this area. I go down to 1.5. All right, and then I say 1.50. The hundredths place is 0, which means our probability now is 0.9332. What if I ask probability of getting less than 0.75? Well, I go down here, 0.7, and then I need the 5, which is right here, 0.75. So that area is 0.7734. If I ask what's the probability of getting a value greater than 0.33, well, I can do 0.33, here's 0.3, here's 0.33, but that's to the left of the line. I want to the right of the line, so I go down to our bottom table, and I get 0.33, 0.3, and then there's our 300ths, and I get 0.370.
Couldn't you just subtract it from 1?
Yep, you can definitely subtract it to 1, because again, the area under the curve equals 1. This 0.3707 is this one's mate, is what I'll call it. So 0.37 whatever plus 0.6293 gives us 1. So yeah, you can do 1 minus to get this value, or you can use this second table. And the other table works very similarly. All right, so here's an example. If our wing length of roaches follows a normal distribution with mean 15, standard deviation of 2, then what's the probability we would draw an individual that's less than 18? All right. What we should notice is that we don't have a 0-1 distribution. All right. We've got a 15-2 normal distribution. So what we're going to have to do is first convert our distribution to a 0-1. And what that means is this. We're going to take, so this is what we're trying to find. We're going to subtract both sides by our population mean, and then we'll divide both sides by our standard deviation. So here's our x minus our mu over our sigma. All right? So that is our conversion to a z. There's our z. And we're asking, what's the probability that we get x less than 18? Well, 18 minus 15 over 2 converts it to 1.5. So now we're asking, what's the probability of finding a roach with a wing length that is 1.5 standard deviations above the mean or less? So there's our z. So what we would do is go back to our table. I think we already did one. Did I do one? I did do 1.5. So 1.50 gives us 0.9332.
How did you do the conversion again?
So we have to use our z equation. So the z is equal to our x minus a mu over sigma. This. That gives us z. But if we're going to do that to the left-hand side of our equation, we also have to do it to the right-hand side. And our mu and our sigma comes from the population. So we took this value, probably a little bit easier, trying to do here. So we've got the probability that our sample is going to be less than 18. Well, I'm going to subtract our mu over the sigma. And our mu is 15, our sigma was 2. So when we do that transformation, that is equal to z. Because z is equal to x minus mu over sigma. And this is 1.5. And now once we have this, we know z approximates a normal 0-1 distribution. That's just defined. So do it to one side, we have to do it to the other side. And this gets us into the situation where we can use our table. All right, this gets us to a situation where we can use our table. All right, so we've got these additional practice problems. I'm going to leave that for homework that you can kind of work through and think through. We're going to do it the same way, right? Because in each of these questions, I give you the population. I give you what the population mean and standard deviation is, and then I ask, what's the probability that something would happen? We get a value larger or smaller. And notice that all of these questions would be larger and smaller than something, or between two numbers, because we're actually working with the area under the curve. So I ask, what's the probability that we actually get, like this first one, we actually find a worm that is 33 millimeters? It's going to be effectively 0, but we cheat by saying, okay, we're going to look at like between 32.9 and 33.1 to get that thin slice. So I'm going to leave that for homework, kind of work through it, use the table, and then what we're going to do is come back and work with these in R to check our answers. And I'll show you how. It's actually fairly easy to do in R. All right. So that gives us time where I can pass this back. I'm going to pass these back. I do have the key. So what you'll have to do to get the total grade. So I wrote this part 1 was out of 34 points. All right. And part 2 was out of 40 points. So to get your total grade, you're just going to add up the totals. So it's out of 74 points. So add up whatever you get on part 1, and then check Blackboard for whatever you get on part 2. That's your total grade for that first exam. All right. Questions? All right. How do I get these passed